27 to the 5/7.
Jackie, why are you back there?
Okay.
Alicia,
Is that our answer? Because I want this written, the instructions say on this, and I didn't copy the instructions, but they say write it in its simplest form.
No.
Well, okay, we could, but even then, you're right. But even then, we could get simpler than this.
You could just do it. 27 with X.
9 to the 3rd.
What?
Okay, what to the 3rd?
9.
Not 9. What is it?
3.
Yes, okay, here's the moral of the story, yeah. The 27 can be written as, it's a perfect cube. So it can be written in terms of a smaller base, right? 27 is a big base, we could make that a smaller one. If I just replace the 27 with a 3 cubed,
How does that make it better?
well, because it makes the base smaller. That's better. We'd like to write it in terms of the smallest base we can if it's simple.
That's not simple. 2 times 5/7.
Okay, yeah, you're right, but we're not done. Right, exactly. So now if I take a power to a power, what do we do to the exponents? Multiply. So what's 3 times 5/7? Ah, good.
That's not simple.
And that is it, right?
So it just says, that's complicated and then we multiply that.
Yeah. Okay, yeah. So that's our answer. Now, we could also, if we chose to, I don't know why you would, but you could also write this as a radical if you wanted to. Boys in the back, this up here, please. Thanks. So if we wrote that as a radical, this is the index of the radical, isn't it? The 7. So we'd write this as a 7th root of 3. What do we do with the numerator?
Put it above the 3.
Yeah, it's the power of the whole thing, right?
So why are you
Okay. Yeah, I think isn't that better just to write it like that?
Yeah.
Okay.
So what assignment is this?
7-2.
7-2.
What
about 7-1?
7-1 is
Really
7-1 is
easy.
it's just evaluating. Yeah, very easy. All it is evaluating radicals, solving some simple equations. For example, what if you wanted to solve this? What if you had x cubed plus 1 equals 28? What would you do?
Subtract
3,
1
subtract
and then
1,
cube root it.
cube root it, and get
Your answer.
my answer. But because it's an odd root, I don't have a plus or minus, right?
Right. That's
So I would just get x equals 3 when I do that. So that's all. I mean, just that stuff.
Super easy.
Not a big deal. Moving on. What about that?
Divided. You subtract
Okay.
It would be it would be
-1 over 3. Subtract the exponent.
Okay, this looks pretty ugly. Let's talk about this strategically for a second. One thing, we always, if we can, we'd like to be able to write a quotient of powers in terms of like bases. If we can write it in terms of like bases, it makes life much easier. Yes, sir.
25 to 5 goes
Say it again.
25 to 5 goes.
Yeah, okay, right. In fact,
Which one would be easier?
in fact, what is 125 in terms of 5?
5 is cubed.
5 cubed. Yeah, exactly. So we could trade the 125, we could write in terms of a smaller base. Okay, so that becomes
5 cubed is 5 to the 4.
Okay, what about 625?
5 to the 4.
5 to the 4th. You see that? If you know that 125 is 5 cubed, it's pretty easy to see that 625 is 5 to the 4th, because it's just 5 times 125, right?
Can you just cancel that, like 3 of the 5s? Or can you not do that?
Well, okay. Unfortunately, you can't do that because they're taken to other exponents, but it's going to be helpful to us. Something good's going to come out of this. So then this 625, we can write as 5 to the 4th to the 3/13. Okay, and so how could we simplify the whole numerator then? Well, if I have a power to a power, how do I simplify that? Multiply it. good. So on the top, we get, boy, this pen, it's almost out of virtual ink or something, I don't know what's going on. So, what about the bottom, what do we get? 12 thirteenths. Okay, so, let me write that, I'm gonna write that down here. Okay, that's better. Now we've got a couple things we can do here. Let's do this the easiest way we can. So we have like bases, correct?
Yeah.
So now I can subtract exponents. But the problem, if we look ahead here, where is the base going to end up?
On the bottom.
On the bottom. If I just subtract if I follow my rule and keep the base on the bottom, I'm going to get 1 over 5 to the, how many 13ths? 6 13ths.
How'd you get 1 on the top? Yeah, we're just one.
Because remember our rule of, now, ignore the fact that these are fractions, because the fractions are just numbers. This is just an application of the rule a to the m over a to the n. If m is bigger than n, remember we keep the base on the top and write it to the m minus n. But if n is bigger than m, remember what I told you to do? It's easier to do is just keep the base on the bottom and subtract the top exponent. So we get,
What happened to the 5?
It goes to the bottom.
well, that's our base.
Is it connected to the 6 and 15?
Yeah, it's to that power, right? In this case, a is equal to 5, right? So we're getting 1 over a to the n minus m power, right? Okay? But that's still, we're not done. What's the issue with that? I mean, those darn mathematicians, they don't like to have those radicals on the bottom. You gotta rationalize the denominator still. Yes, sir? Okay, good. We need to get an integer on the bottom. We can't have a radical, so we'd have to multiply top and bottom by some number of 13ths. That's gonna give us an integer exponent on the bottom. Okay, so that means multiplying by top and bottom. Get rid of this stuff. Top and bottom by 5 to the 7 13ths. Right, so I end up with 5 to the 1 on the, everybody see that? I get 5 to the 13 13ths. So I just get a plain old 5 on the bottom and 5 to the 7 13ths on the top. Okay, that's fine. But remember we said there's an easier way to do that. We could really skip a step there. We didn't really have to do that part right there. That wasn't really strictly necessary, was it? We could have instead, let's just go from there. So we had 5 to the 6 13ths over 5 to the 12 13ths. We can already see, as good mathematicians, we can already see that the exponent on the bottom is bigger, so we know we're going to be stuck. We're going to have to rationalize the denominator, right? So instead of going through that intermediate step, what's maybe an easier way to get a 5 to the 1 on the bottom? Yeah, how about if we just instead just multiply top and bottom by 5 to the 1 13th, right? Does that make sense? And then on the bottom, we're going to get our 5 to the 13 13ths, 5 to the 1.
Well, that makes sense, because 7 over 13 was just such a random number.
Yeah, but now we can see where we get it from, right? 5 to the 6 13ths plus 1 13th. There's our 5 to the 7 13ths. Make sense? Yes, ma'am.
So you just try to complete the larger
Oh, this makes more sense.
integer.
Right. This is the equivalent. Remember, this is the equivalent of what we did back in chapter 5 when we had a stranded radical on the bottom, stranded square root. So for example, if we had something like 3 over square root of 5, we multiply top and bottom by square root of 5. Okay?
That was very nice of you.
Yes?
What is the radical, or, yeah, no, not the radical,
The base?
No, the exponent on the bottom was over the over the denominator of the exponent, like the numerator one. Like what if there was like 14 or 15, 16?
So, say it again, so if you had,
It goes like 5 to 14, 13.
on the bottom?
Yeah.
Oh, okay, if it's 5 to the 14/13, good question. So, yeah, I like that, it's a good question.
What was that? Was that it?
Your students love
What was that?
Okay, so,
He virtually did not.
He looked like it.
He looked at them.
okay, so, what about this? I mean, there's a bunch of ways we could resolve this. Okay, first of all, we could do what we did last time, the first time, right? That was kind of inefficient. We could just subtract the 6/13 from the 14/13 on the bottom, right?
No, I don't.
But we don't want to do that.
Oh.
So how could we multiply by 5 to some exponent so that on the bottom we're going to get 13/13? Yeah.
Was this our answer?
Yeah, that was our
That
answer.
was- okay.
That's our answer. Yeah. Yeah. So this is this is our answer. Why is that better? I'm not going to claim that it is, but this is simplest form because we don't have a radical on the bottom.
Okay.
Okay.
So
Right.
you're allowed to have a radical on top.
Yes, but not on the bottom. Because remember that a 13th root, if I have a fractional exponent with a 13 on the bottom, that's equivalent to a 13th root, right? So that counts as a radical.
Okay.
Okay, what about here? Could we use the same trick? Sure.
Yes.
We'll just multiply top and bottom by 5 to what power to get 13/13 on the bottom?
-1.
Negative 1/13. Sure.
That's not a real thing, is it though?
Sure.
You're trying to make 13 over.
Yeah, okay. You tell me, what is, real quick, what is 5 to the negative 1/13? Written as a radical, how about?
-5?
What's the negative do?
It makes the radical,
What's the radical?
Puts it on the bottom, right? So this just becomes 1 over 5 to the positive 1/13, which would just be 1 over the 13th root of 5. So it is something.
Okay.
Okay. Now what do we get when we use this trick? So on the bottom we get our 5 to the 13/13. What do we get on the top?
-7.
5 to the 5/13, because we're adding, right? If we multiply like bases, we add the exponents. So 5 to the,
5.
good question. Yeah,
That is our answer.
that's our answer. Okay.
Ugly. 5 times.
Okay.
Why can't you? Oh, never mind. So that one would be 5 to the 5th under the radical is 13.
13th root of 5 to the 5th.
Oh, okay.
Okay? That looks terrible, but I want you to see that this is really just the same thing we've been
Yeah,
doing.
you just write it differently.
Yeah, exactly. And here's the other kind of the moral of the story. Don't freak out about fractional exponents because they're just exponents. And true, this last example we did is something that we wouldn't have dealt with in chapter 6 when we were dealing with integer exponents. So this is kind of a new wrinkle that we get that's added because of the fact that we have fractional exponents. Now, we wouldn't have had this problem though if the top had been like 5/13 or something. Like I say, let's say on the top we had the 12/13 and the bottom was a 6/13. Wouldn't have been a big deal. Because then we would have just subtracted, right, and had a radical on the top, and that's fine. The only issue we had here is because the bottom had a bigger power of our base than the top did. And we had to do all that weird rationalize the denominator stuff. Okay, but then the other moral of the story, question on that last one?
Yeah. Sorry.
That's fine.
So you'd have to make the bases or whatever smaller first, because if you look at that,
Yes, yeah, you do, because now, we really don't have a way to simplify an expression involving rational exponents unless we either can get like bases or like exponents, right? And in this case, like bases is always preferable, it makes it easier, okay? The other thing I want you to remember is that when you see these funky radical expressions to simplify, just turn them into, it's easy to do, just turn them into rational exponents and use properties of exponents, right? These are much more complicated to think about, at least initially. Eventually, you'll probably get to a point where you could maybe do this without having to turn it into rational exponents. But that takes some practice. You're a ways away from that, I would guess. So all we want to do is just turn these into rational exponents. So what's this one going to become?
7 over 19.
2 to the, now what's the denominator going to be?
19 over
19. And what goes on the top?
7.
Oh, sorry, I got it backwards.
Yeah.
Got it backwards.
So when we're solving these, we need to like, put it out like this.
Yes, that makes it easier, because then you can use all the same stuff that we've been talking about. It makes the problem just like the ones we've been doing. Remember that the index of the radical always is the denominator of the fraction. And the answer can be 8, you're right. 2 to the,
2 over 7.
so we get like bases, it ends up being easy. We get 2 to what power?
21. 2 to the, can't you divide 3, right?
Yeah, let's do cube.
Hey, I got it like 6 minutes after you.
After you mean before?
No, after.
Okay, this is kind of a doozy though. I want to be one really, this one's kind of a doozy. Okay. I mean, it's not terrible. There's a way we can go about this that makes it easier. Yes, sir. Yes, yeah, you can. Now, what might be, now, what we could do, what if this were, this would have been a really simple problem if that were an 81 over 9. How come?
Because you just divide it.
Yeah, we could simplify inside the radical and make it simple, right? Unfortunately, that's not what it is though. So what we want to do here then probably is this 1/4 power, or the fourth root just means a 1/4 power, right? So we can write this as what to the 1/4? 80 over 9. Okay. All right, now what we'd like to do here is we would like to see if we can, our goal, remember, is to get as much out of the radical as possible. That's one part, but we also have to get the radical off the bottom. Agreed? Okay, so what about the top, 4th root of 80? Is there anything we could get out of the radical? Remember our trick for that. Our trick for that is we want to break the 80 down if we can. If it's not prime, which it's not, we want to write it in terms of smaller bases, okay? So what is 80? 80, if I factor it, equals what? 2 times 40, and 40 is 2 times 20, which is 2 times 10, which is 2 times 5. So I get 1, 2, 3, 2 to the 4th times 5, right? Everybody see that? So this becomes times 5 to the 1 over, on the bottom we're going to get, yeah, 3, if we want to write it as 3 to the 2nd, that's fine, we can do that too. Okay?
And then we just define this.
Right, so, okay, so how does that help us on the top?
You get 2
Yeah, okay, if I distribute the 1/4 on the top, look what I get. On the top, I'm gonna get 2 to the 4th to the 1/4 times 5 to the 1/4. What's 2 to the 4th to the 1/4?
1, 2,
2,
why?
right? Because it's 2 to the 1. If I take a power to a power, I multiply the exponents. 4 times 1/4 is 1. 2 to the 1
Oh, I see.
is 2, right? Okay, what about the bottom? Well, on the bottom we get, what, 3 to the 2/4?
Yeah.
Okay, now, I want you to be careful with this. There would be a real temptation there to write that as 3 to the 1/2, because it is, right? That is 3 to the 1/2, but what's key here is that we need to have, right, we need to be able to have because we don't have like bases, we gotta be able to write this as a like radical at the very least. We need to keep the denominators the same, right? Here's why. Look what we end up with. On the bottom, we get 3 to the 2/4. And so, what do I have to do to get rid of that 3 to the 2/4 on the bottom? Multiply by 3 to the 2/4, top and bottom, right? Everybody agree? So now look, that's not a big deal though. It's gonna work out fine for us if I do that, because I've got these fractions that have like denominators in my exponents. Look what happens. So on the top, we end up with 2 times what's 5 to the 1/4 times 3 to the 2/4. Okay, yeah, isn't that the same thing? Now look, this is the same thing as saying, if I factor out a 1/4, because I can do that, right? I can factor out, if I have a product of powers, I can factor out a power, right? So I can write that as 2 times 5 to the 1 times 3 squared to the 1/4, right?
Why did you do that?
Because otherwise,
It doesn't matter before.
well, I wouldn't have to do it in that order, but even if I just added these up, well, I can't add them up, they're not like bases.
Okay.
See what I'm saying? So I've gotta be able to write this in terms of a like exponent. Okay, the other way I could have maybe done that is not written that as a 3 squared. Then it would have been 9 to the 1/4. Everybody see that? If I have 5 to the 1/4 times 9 to the 1/4, isn't that just 5 times 9 to the 1/4?
Yeah.
That's all 3 squared is though, right? Get the idea? Okay, on the bottom, what do we have?
9 to the 4.
Well, we have 3 to the 2/4 times 3 to the 2/4 is 3 to the 1.
There's 3.
Why isn't it 9?
Why isn't it 9? Because our rule says if we multiply, remember this is our rule of exponents, a to the m
Oh, yeah.
times a to the n is the same base to the sum.
So is that why you don't change 2 because it doesn't have the same?
Say it again. Yeah, the 2, what do you mean? This one out front?
Yeah, is that why you don't change it because it doesn't have the same exponent?
It's already out of the radical. See, look what happened up here. The 2, when we distributed the 1/4, 2 to the 4th to the 1/4 is just an integer 2. It's not inside, it's free. It's outside, right? It made it out of the fractional power, out of the radical. See
Do
the
you have to
difference?
simplify it from there?
Yeah, what is this? What's 5 times 3 squared?
15.
No, 5 times
45.
45. And so that's our answer.
2 times 45 to the 1/4.
Right, that's
And
it.
the 1/4 being the parentheses?
Well,
Wait, that's it?
that's it. That's it. Now, if we want to write that as a radical, that's just 2 times the 4th root of 45 over 3. We can't go any further, can we? Because the 4th root of 45 is not a perfect, right? It's not a perfect fourth, and it has no perfect fourth factors. Okay, so we're stuck. Yes?
So, are you gonna tell us to write it one way, write it the other way, or is it?
Either or is fine. Yeah, it doesn't make any difference. Those are both equally good. I prefer that way, but either way is fine.
Which way do you prefer?
I prefer to write it as a fractional exponent myself. But either way is fine. Okay, I mean, on a couple questions, I might ask you to write it, for this question, write it as a radical or this, but in general, no, doesn't make a difference. Okay, does that make sense?
Yes.
Once again, if you go back and look at our strategy, think what we did here. We just simplified the top, and in simplifying the top, we got a 2 out of the top, didn't we? We got a 2 out of the 4th root on the top. We're left with a 5 inside the radical. Okay. On the bottom, really there was no point, and in hindsight, you see this, in hindsight, we really didn't even need to write the bottom as a 3 squared. It probably would have been almost easier to think about if we just wrote it as a 9. Right, if we just wrote that as, just left it as a 9.
So you times that by 1.
would have just we just would have multiplied by 9 to the,
Should be 2.
yeah, so we would 9 to the 2/4, which is square root of 9, which is 3, right? Worst case scenario, if we multiplied by 9 to the 3/4, we would have we wouldn't have been able to reduce the fraction a little bit, but big deal. We can't reduce this fraction though, because 2/3 doesn't reduce, right? But what if we'd had something like 6/9? We could have reduced that a little bit, right? So it's not like there's one way to do these. I'm just trying to show you the most efficient way to do these. But you can apply these, you can apply these properties as long as you apply them correctly. There are just, literally probably an infinite number of ways you could do this problem. To me, this is the easiest way. Okay. All right. What about something like that? And keep in mind that last one that's kind of the granddaddy of all radical problems. That was pretty tough.
Yeah,
What about this one? This one looks harder, but it's easier. You'll see. Go ahead.
3 to the, was it 3 cubed?
Okay. So now
And 3
what you
squared.
might notice here, good, is that the 9 and the 27, one's a perfect square, one's a perfect cube, right? So we'd like to write this in terms of smaller bases if possible. Okay, well, what does the top become? If I want to write that, so it's 3 squared,
To the 1
3 to the 2.
3 to the 2/3. Everybody agree on the top,
Why?
right? Because we get 3 squared to the 1/3.
Wait, 3 squared to the 1/3.
Does that make sense?
Yeah, so then why don't we put 3 squared?
Oh, we could. The 9 is just a 3 squared, right?
Yeah.
Okay.
Oh,
The 1 times the 1/3.
To the 1/3 power means you multiply by 1/3.
But could you do 3 squared
Oh, I
in
see.
parentheses and then do 1/3?
Yeah, sure. Yeah, either way. What about the bottom? 27 is really just
3 to the 3. So
3
3
cubed.
and 3/5.
Yeah.
3
So
to the
3 to the 3/5. Okay, so what do we do? What's bigger, 2/3? We have like bases, so this ends up being easy, right?
Oh, yeah.
Threes,
Oh, yeah, we do.
right? So what's bigger, 2/3 or 3/5? 2/3. Good, so this will be an easy one. We'll just subtract on the top, right? So we get 3 to the 2/3 minus 3/5. What is 2/3 minus 3/5 if I get a common denominator? How many 15ths do I get here? 10. How many here?
15.
9. So 10 15ths minus 9 15ths. That's our answer.
Wait, isn't there 3 on the bottom?
But when we divide like bases, we subtract the exponents,
Okay.
right? You everybody see
But
that?
on the other one, the 5 just stayed on the bottom.
Okay, but we made it stay on the bottom. Remember the difference in the last case was we had a bigger exponent on the bottom, right? And so we had to leave the base on the bottom, so we needed to rationalize things also. Okay? We looked out here. If the exponent on top is bigger, we don't have to worry about having a stranded radical on the bottom. We just get our answer.
And that was just 15 squared.
15, this is the 15th, if I want to write it as a radical, it's just the 15th, boy, that pen's on good, 15th root of 3. Okay. All right, what about, we'll come back to that one. We just did one similar to that, I just wanted to give you a little more practice on hard one. Okay, what about this one?
You take out you got 592, and then you can take out the multiples.
Okay, good, so this one, far and away, the hardest part of this one is the 192. Okay, really this is the trick that I showed you guys last week. This is the greatest trick ever. It turns this into a really simple problem. If you're dealing with the exponents, we can take care of those right now. Right, we've got something outside times something inside. Well, what power of x do I have there? If I have a 5th root of x to the 9th, that's x to what? 9/5, good. So x to the 9/5 written as a mixed number is what? 1 and 4/5. So what's the power of x outside the radical? 1. So we're gonna get an x to the 1 outside. What's the power of x inside the radical? 4, because inside we've got 4/5, right? Remember that the index of the radical is always the denominator of the fraction. So this is really just 1 plus 4/5, 1 4/5. What about the y's?
You got 15.
15 over 5, which is y to the third.
Okay, and that's not even a mixed number, that's just a straight integer, right? So then what's the power outside? 3. That's it, yeah. Okay, what about the z?
3.
Yeah, so that's not a mixed number, there's no integer part of the mixed number there, right? There's nothing outside, inside we just are stuck with 3/5. So the hardest part is the 192. We have to simplify the 5th root of 192. Okay, remember that's just 192 to the 1/5. Okay, so we gotta break 192 up, and we have to factor it, see if we get some good stuff happening. Okay, so 192, what are the factors of 192?
2 and 81. I don't know. I just guessed.
96.
96. Okay, and 96, what about 96?
2 times 48.
Okay, so 48, so 2 times 96, which is 2 times 2 times 48. Well, 48 is 16 times 3, right? Okay, so 16 is 2 to the what? So we can maybe cut to the chase here. So we get 2 times 2 times 2 to the 4th times 3. What power of 2 do I have there?
2 to the 6th.
2 to the 6th, exactly, right? So, long story short here, we could break this up into 3 times 2 to the 6th, okay? To the 1/5. Okay, so let's figure out what part goes inside and what part goes outside then for our square root of, our 5th root of 192. Okay, so if I distribute the 1/5, what do I get? I get 3 to what power, I guess?
3 to the 1/5.
3 to the 1/5, so I'm gonna get a 3 stuck inside, aren't I? Yep. Right? 3 to the 1 inside. What about the 2 to the 6/5?
You're gonna get 2 outside and 2 to the 1/5.
Ah, okay. So if I look inside, if I write this as a mixed number, I get 2 to the 6/5, which is 1 and 1/5, right? So I'm gonna get a 2 to the 1 outside and a 2 to the 1 inside, right? Okay, this becomes, look at what these become. I get a 3 to the 1/5 times 2 to the 6/5. Remember our rule. If we write a base with a fractional exponent, if we write that as a mixed number, the integer part is the power outside, right? And the fraction part represents what's stuck in the radical.
Wait, why did you break it up? I mean, it already said 2 to the 6.
Yeah.
It just seems kind of unnecessary.
Maybe, like, what are you suggesting, Zoe, right here?
You had it 3 times 2 to the 6, and you broke up the 2, and you just put it back together.
Down here, you mean? Oh, that's old work. Yeah, we don't need that. You're right. That was what, I kind of rewrote this up here.
Oh.
Yeah, there, maybe that's better. Okay.
So
You're right, that would have been reversing all our hard work. Okay? Everybody see that? So the 3 gets stuck inside, but the 2 to the 1/6 is the same thing as saying 2 to the 1 and 1/5. So that's the part that goes outside. And this is the part that goes inside. Right? Just like we did with the exponents. Same deal.
So do you
If we had an
combine
x to the 9/5, you guys all told me that's x to the 1 and 4/5, right? Well, what if it's a 2 instead of an x? If I have a 2 to the 6/5, that's 2 to the 1 and 1/5, right?
Do you write the answer with the 2 different answers?
So we get the 2 outside,
Oh, you added
Yeah. and now what goes in here?
2.
6. 3 times 2, right? That's what was left from the 192, that's the stuff that was stuck in the radical, was a 3 to
So
the
you
1
have
and a 2.
two answers?
No, that's our answer.
Oh, yeah, I know. Technically.
This was just our way of kind of trying to figure out how do we deal with the fifth root of 192. Here's our work, this is our answer that we're gonna plug back in with the other stuff.
Could you scroll up a little bit?
Yep.
It looks still.
Yeah, that one was.
Okay. How about another one of those? That sound like a good
No,
idea?
we did it.
Okay. Okay, let's try another one. How about, let's try,
Because I don't get 6 to the 5th, how that's divided.
okay, what about the variables? What about the, what power of x do we have there? X to the
16 thirds.
16 thirds is a mixed number. 16 thirds is what?
X to the 4 and. Oh, I don't get it.
X to the 5.
Mixed numbers are weird. Can you do that math? for
Sure.
me?
X to the 16 thirds. So 3 goes into 16, 5,
Okay.
and 1 left over,
Okay.
Okay.
Oh. Okay.
right?
Now.
Okay, what about the y's?
7
Y, you got a 7 on the outside.
Okay, I get y to the 21 thirds, which is an integer. That's just a 7. The integers go out, right?
Yes.
So we get y
Okay.
to the 7th, totally outside. What about the z?
You got 5 inside, C squared. Or 5 outside, C
Yeah.
squared inside.
Yeah.
Z to the 17 thirds is a mixed number. 17 thirds is 5 and 2 thirds. Right? And there's our denominator. There's our 3, right? Okay. Now the ugly part. Really the worst part is the number. So we got to simplify the cube root of 343. So 343, let's try to break this down. Let's try to be a little more efficient with this. See if we can break it down into a base to a big power.
Yeah.
Okay. Times something else. Well, 243 is 3 to what? What's real quick? What's 3 to the 4th? It's really easy to find. 3 to the 4th is just 3 squared squared, isn't it? So 3 squared is, yeah, it's 81. So then 3 times 81 is 243. So 243 is really just, we could rewrite that as 3 to the 5th, right?
Yeah.
So what we've got here is the cube root of 3 to the 5th. That's 3 to what power?
5 thirds.
Yeah, 3 to the 5 thirds. Now that's the same thing as saying, focus please. That's the same thing as saying 3 to the 1 and 2 thirds, right? 3 to the 1 and 2 thirds. Okay, so we get a 3 outside, and inside we get a 3 to the 2 thirds. But what's a 3 squared? 9. Exactly.
Okay.
Okay? Right? So we replace that with a 9. Okay? Make sense?
Yes.
Okay.
Will we have lots of like
God, my head is
involving
so
all
much
those
earlier.
like that?
No, those are the hardest ones I
Oh.
have. I mean, I might give you one of those, maybe. That's it. Mostly they'll be. Those are really supposed to be pretty hard problems, but if you use that trick, they're not so bad. Yeah. Okay, so I want to ask you a question here. We got to talk about some cool math for a second.
We got like 3 minutes.
Is that all we have?
Yeah.
Okay, let's not. I got to take a roll.
Yeah.